Hey everybody, in this video we're going to be looking into transformers. Transformers are used to change the voltage and current in circuits. They are widely used in power transmission and for household appliances. A transformer is made up of two coils wrapped around a laminated soft iron core. This is our soft iron core, and it is made up of laminated sheets of that soft iron. Now having a side-on view of our soft iron core, so instead of having a solid block of iron, we have sheets of iron that are separated by different chemical components. Some can be just a silicon based, others can be manganese or aluminium. It all depends on the situation. The main reason for this is that it breaks up the eddy currents produced in the solid piece of iron, thus allowing less heat to be developed inside of our core. Next we have a coil of wire. The primary coil is connected to the AC source. The secondary coil is the changed current and voltage for the new circuit. So how does a transformer actually work? So our primary coil is going to have an alternating source. Its electrons are going to move backwards and forwards and produce a magnetic field inside of that soft iron core. Our magnetic field is able to move around our soft iron core. As the alternating current in our primary coil produces a changing magnetic flux in our soft iron core, this then induces an EMF in our secondary coil. This simulation shows a basic transformer setup. Even though they are not connected to each other, there is an induced current in the secondary circuit. So how are we able to determine what sort of electrical flow is produced from our transformer? Well, we know from Faraday's law that the EMF of the primary is going to be equal to the number of coils of the primary times by the changing magnetic flux. And that the EMF produced in the secondary coil is going to be equal to the number of coils times by the changing magnetic flux. As our transformer is all connected by the one soft iron core, the changing magnetic flux is actually equal to each other. This means that we can make them equal to each other and arrange our formula in such a way that the EMF produced in the primary divided by the EMF in the secondary is equal to the number of turns of the primary over the number of turns in the secondary. If the secondary coil has more coils than the primary, it is a step-up transformer. As you can see in this simulation, the EMF produced in our secondary coil is higher than that of our primary coil. However, the current produced is less. If the primary has more coils than the secondary, it is a step-down transformer, which you can see in this simulation. Our EMF is less than that of the primary, however we do have a higher current. If a DC power supply is connected to a transformer, there is no change in magnetic flux. Thus, there is no induced EMF in the secondary coil. All what we've so far been talking about is for what's called an ideal transformer. This means that there's no power loss from anywhere in the system. However, this is not realistically true, as the induced EMF and the changing magnetic flux will produce eddy currents, even with our laminated core. And any transformer, due to this, will actually generate heat. Think about your mobile phone charger at home. After a while of it charging, you can actually touch the charger and it will feel warm. Next, we need to see the relationship between the current and the number of coils. When we were looking at the simulations, when we had a step-up or a step-down transformer, the current behaved in an opposite manner. In fact, it is opposite. If we had our number of turns of the primary divided by the number of turns of the secondary, it would be equal to the current flowing in the secondary circuit divided by the current flowing in the primary circuit. So this gives us the relationship between the current and the voltage for transformers. Transformers are also hugely important for the production and transmission of electricity. As power plants are huge distances away from our homes, the power needs to be transferred with the least amount of power loss. As any wire has some resistance, we need to limit the amount of power lost due to that resistance. So how are we going to do that? We know that power is equal to the current times the voltage. We also know that from Ohm's law that voltage is equal to the current times the resistance. Rearranging and substituting, we get that power is equal to the current squared times by the resistance, and we also get that power is equal to the voltage squared divided by the resistance, where R is the resistance of our wires. We can see by this that if we have a higher current flowing through our wires, we're going to end up with more power loss. If we limit the current flowing through our wires and have a higher voltage, we can decrease the amount of power loss. In fact, the large power lines coming from our power stations have about 66,000 volts as a root mean squared average. In summary, we've talked about the composition of a transformer, its primary and secondary coils. We've looked at how the EMF and the number of turns are related. We've also looked at the relationship between the number of turns and the current flowing through. We've also talked about how having a higher voltage and a lower current for power transmission is going to help limit the amount of power loss. Thanks for watching. See you in the next video.